Okay, so I believe that we were in this place. Yeah, the proof in the previous lecture, and then okay, so today we start with intersection graphs. So what is intersection graph? So you have let us say a finite set, not necessarily finite actually, but we have a finite set, and a set of subsets, or family of subsets, let's say F. So you have a set V and a family of elements from V, like a family of sets which are subsets of V, which form this family F. Now, once you have this family, you can actually define some graphs related to this. So one natural way to define a graph is to define a bipartite graph, where you have a set, the set V on one side and the set F on the other side. Then whenever an element belongs to a set in the family, you put an edge. This is called the incidence graph of the family. This is one way to define a graph. This will contain all the information about the family itself. But there is another way to define a family, define a graph from this family, and that is what is called the intersection graph. So what you do here is that, like, you have this family of sets F, and then if two of the sets in this family are intersecting, then you put an edge between the corresponding vertices. So we will make the elements of the family as vertices, and then you put an edge if the corresponding sets have non-empty intersection. So this will give you a graph, and it's called the intersection graph of this family. So here is an example where you have the set V to be A, B, C, D, E, F, and G, and then you have the family F as this sets. DFG is the first one set, then BDF, BCD, ACE, ACF, and EFG. So you have these sets in the family. So to make the graph, I define I define these sets as the vertices of the graph, right? So you have this you have this uh, you have this vertices, which are the elements of the family, and then whenever there is a common element, for example, B is common to this, so I have an edge. Similarly, F is common to this, so there is an edge here, or D is common also. And here, similarly, all these edges are there. So I have a graph from this. So this is called the intersection graph of this family. So now one interesting question to think about: which graphs are intersection graphs, or which graphs have an intersection representation, right? So representation as a intersection graph of some family. So you can think about that while we go to look at another special case of this. So let us say that we have the vertex set of a graph, which called as V, right, for to define the family, and the edge set of the graph is is F, which is the actual family, right? So edges are basically two element subsets. So therefore now we have F as basically the set of edges. No, if you look at this family, right, V is the set of vertices, right, and then of course the The family F is defined on, as the subsets, two element subsets of the set V. So we have this set system, and then the corresponding graph that we define, as the intersection graph that we define, is having the edges as the vertices of the graph, right? That's what we do, right? We have the elements of the family as the vertices, so which means that the edges as the vertices, and two elements, right, are adjacent. Two vertices are adjacent if in this case the edges are the vertices of the new graph, right? And they are adjacent if they have a common endpoint, right? These two edges have a common endpoint, then you make them adjacent. So this graph is is actually called the line graph because it was defined in a different context, and then it's usually denoted by L of G. So given a graph G, we can define what's called the line graph. But the line graph is the graph where the edges become the vertices, and two vertices in the line graph are adjacent if the corresponding edges have non-empty intersection. So we have graph G, right? So this is graph G, right? And what is the line graph of this graph? So we have the edges of this graph are 1, 2, 2, 4, 2, 3, 3, 4. So 1, 2, 2, 3, 2, 4, and 3, 4 are the vertices of the line graph. And the adjacency is if there is some common element, right? So we have 1, 2, and 2, 4, and then 1, 2, 2, 3, 2, 3, 3, 4, 2, 1, 2, 3, and 2, 4, and 3, 4. So we get the line graph of the graph, and so you have this, this graph and its line graph. Then you have another graph here, right, which is the star graph, right? So you have 1, 2, 3, 4, 5 are the vertices. One is the center of the star, and the corresponding graph. You know that any two edges in the star are adjacent, so therefore the edges, any of them have non-empty intersection, and therefore in the line graph you will get a complete graph. So if you take a star graph, then the line graph is going to be a complete graph because any two edges are going to be incident to each other. So now one question one can think about is that is it true that all the graphs are line graphs of some other graphs, or like are there graphs which are not line graphs of graphs, right? And one can ask this and think about such things. Then another question one can ask is that, like, is the line graph uniquely defined, or if the line graph is given, line graph is unique, but if the line graph is given, can you find out what is the graph that you started from, right? Which graph is the graph for which is the line graph. Now this example here that I have shown tells you that it is not exactly clear whether we can do this, right? So for example, the triangle graph, right, which is the complete graph on three vertices, its line graph is also itself, right? So it's the triangle graph on three vertices, right? And on the other hand, the star graph with four vertices, its line graph is also the triangle or the complete graph on three vertices. So this makes it kind of wondering like whether there are other graphs which have this issue, and then you can think about this. I will not discuss it at the moment, but it will be a nice exercise to think of and try to see if you can find other graphs, a pair of graphs whose line graph is the same. So all these things, it is important to think about these questions. And if I try to discuss it now, then you won't be able to think about it. So that is the reason I want to keep some of these things as open questions. Okay, now let us define another type of intersection graphs, which is called interval graphs. So to bring it to a context, let us see an application of this. Okay. So in fact, there are several applications one can mention. I will see if I can find something more to add later. So in this example, we have a computer program, right? And the computer program is how when it runs, basically it keeps the variables in the memory, right? And this values are basically taken from the memory and carried over to the register of the computer, where some kind of computation takes place. So any computation that is going to happen always happens in the register of the computer. So, this value from memory will be copied to the register, then do some computation from, that, and then it will be, the result will be copied back to some other variable or like, something like that. Now, the problem is that like, these registers are very expensive to make. Okay? So if you make a computer, you want to try to minimize the expenditure for making the computer chip. So you want to find out like some kind of optimum number of registers that will be required. I mean, for example, even for a program itself, like it is better to minimize the use of the registers, because if there are several programs running at the same time, maybe right, like it can basically try to reduce the use of this expensive resource. So let us say that we have a variable, then you are basically going to copy it to the register to do the computation, right? Now then the question comes like when are how many registers that we are going to require to run this program. Now what happens when you run a program is that like you define certain variables, then that variable will take some value, right? Then it will run for some time. You will define some other variables in between, maybe, right? That will run for some time, and then once the scope of the variable finishes, that will be basically pulsed from the memory, right? And then you might introduce some other variables. There will be some variables which are continuing. So there is a time for which a variable in the program is basically active in the program. So now we that basically the time in which the variable is active is basically an interval, right? Because it becomes active at some point in the program, then it continues till some point, and then it is basically gone from the program, right? It's finished. So what we do is that we basically look at these variables and how long they are active, right, in the program, and then we define these intervals, right? So intervals in which this variable is active. So variable x is active from this point in the time, right? So if you have a timeline, like this, and then you can say that okay, at this point the variable becomes active, then another variable becomes active, right? And this one is now no more active, right? And no, etc. So we can do this, and then now we know that if two variables are active at the same time, then of course we have to use different registers for it, because you cannot basically put both of them into the same register to do computation. So therefore, what we do is that we will make sure that if we want to find out the maximum number of variables which are active at the same point of time, right? And this will tell you uh, how to allocate the register the registers to the variables, and how many registers will be required and things. So essentially, what we are saying is that we can now define a graph from this interval. So you have these intervals, and whenever two intervals have a non-empty intersection, we we make the intervals as vertices, and whenever they have non-empty intersection, we put an edge joining them, and then we define a graph. And if you look at the chromatic number of this graph, right, that tells you, like that tells you the number of registers that will be required. Now, such a graph that we define, like you have a set of intervals on the real line, and then and this interval become the vertices of the graph, and adjacency is non-empty intersection, and this graph is called the interval graph. So this is also a graph that we can define as the intersection graph of intervals. So here is the formal definition. We define a graph with variables are the vertices, in which two vertices are adjacent if they are active at a common time, right? This is precisely, the definition, like where the intervals will become the vertices, and two intervals are adjacent if they are intersecting. Now, yeah. So we have this kind of interval graphs. Okay. I think I already defined this. So given a family of intervals, we can do this. It's called interval graph. Let's look at some examples. Then try to look at some topics. So yeah, interval, right? So you have an interval A which starts at some point, then till here, and then B which starts here, right? B, C, so. And then if you look at this, you can see that A and B have some intersection, right? So A and B becomes adjacent in the interval graph. Right? Similarly, B and D and B and C are also, right? B, C have common points. So all these edges are there. Similarly, DC and AD. But of course, A and D are, not AD. A and D are not adjacent because they are different timelines. There is no common point. And similarly, you have C and E intersecting, and E and G, E and F and G are. So we get this graph, which we call the interval graph of this set of intervals. So now another question one can think about is that, like, which graphs are interval graphs, right? Or can you find interval representation for all graphs, right? Is it true or not? So here are these questions that I want you to think about, right? Do all graphs have interval representation? Then second question is to give examples of graphs that have no interval representation, if any, right? So if you find that there are some graphs which does not have interval representation, then give some examples for this. And investigate the graphs that are not line graphs of any graph. We mentioned the line graph. So these are some questions that I want you to think about. Some homework questions before we go to our next topic. So a family of sets has what's called the Helly property. If the members of each pairwise intersecting subfamily have an element in common. Okay. So such a family is called is said to possess the Helly property. Now show that the family of closed intervals on the real line has the Helly property. Now, once you once you show this, you can use that property to show that the following graph that I have depicted here is actually not an interval graph. So we have already answered one of the questions that I asked you to think about, but try to again see why this is the case, and then try to come up with some arguments. So show that this graph is not interval. graph by showing that or making use of the lack of value property. Then prove that every graph is an intersection graph for some set system. Okay. So this is another. I mean, it's quite easy actually. If you just think about it, I think you might get it. Very easy. And the third question is to find interval representation of the graphs which are depicted below, right? And if such a representation is possible. So if there is an interval representation of the graph, come up with an interval, a set of intervals for which this is the graph. So that for each of the graphs, and if one of them it is not possible, come up with an argument why it is not possible. Okay. So no, certain classes of graphs have this property that if you take any induced subgraph, okay, so there is a difference between graphs and induced subgraphs. So if you recall, induced subgraphs are basically the graphs obtained by just vertex deletion, right? You cannot just delete an arbitrary edge, but if you just delete vertices, what you get is induced subgraph, because by definition of induced subgraph, we are basically taking a subset of vertices, and the edges between them are present if and only if they are present in the original graph, right? So therefore, basically you are removing the remaining vertices from the graph. So now, suppose you have a family of graphs where if you just delete a vertex, what remains still belongs to the same family, right? So such classes of graphs are called hereditary. Okay, so a family of graphs is hereditary if every induced graph also belongs to that family itself. So there are many examples. For example, if you have an acyclic graph, right? So graph without cycles, if you remove any vertex, what remains is also a graph without cycles, right? So acyclic graphs are hereditary, right? Then if you take a complete graph, right? Complete graph, if you remove some set of vertices, what remains is a smaller complete graph. So the family of complete graphs is also hereditary. Then we have, I think, very briefly mentioned about graphs which can be embedded on the plane, right? Which you can draw on the plane without crossing the edges. Such graphs are called planar graphs, and if you have an embedding of a graph, removing a vertex and the edges connected to that vertex will still keep that same embedding as it is, like except this vertex and edges are missing, right? So therefore, planar graphs are also hereditary. If you remove vertices, it will still be bipartite. You cannot introduce odd cycles by removing vertices, right? So therefore, the class of bipartite graphs are hereditary. Class of complete graphs, then interval graphs are hereditary. So why is interval graphs hereditary? So yes. Yeah, so interval graphs are hereditary because so what is an induced subgraph? It is basically a subgraph on a subset of vertices, right? Now, if a graph is an interval graph, we know that there is an interval representation of the graph, right? Which means that corresponding to every vertex, we can define an interval, right? Such that basically closed interval, such that uh, any two vertices become adjacent only if the corresponding intervals are are intersecting, right? So now let us look at a subgraph of the interval graph, or induced subgraph, which means that you have some subset of vertices. But then if you look at the corresponding intervals, their intersection is intact, right? So therefore, what you get is precisely, another interval graph. So therefore, induced graphs are also, interval graphs are also hereditary, right? Then, we have mentioned what's called k-degenerate graphs. So for us, k-degenerate graphs, planar graphs, etc., hereditary graphs. So these are examples. You think about other classes of graphs which you can come up with, which are hereditary, and try to see how many you can think about. Okay. Now we want to talk about graphs which are perfect. Okay. So we say a graph to be perfect. Okay. So this is basically trying to answer one of the earlier questions that we posed, right? We asked, the relations between the chromatic number and the click number, right? And said that, okay, we know that the chromatic number is greater than or equal to click number. Then we ask, like, can it be arbitrarily large? Then can it be equal, or when are they going to be equal, right? And questions like that. So then we said that, okay, it can be different for and quite quite far apart, right? As large as you want, you can make the distance between the click number and the chromatic number. But of course, there are several classes of graphs for which they coincide. Okay? Now, we say a graph to be perfect if not just for that graph, but for every induced subgraph, we have the property that the chromatic number will be equal to the click number. Okay? So a graph is perfect if and only if for every induced subgraph of the graph, right? We have the chromatic number of the induced subgraph is actually equal to the click number of the induced subgraph. So for any subset of vertices A of the vertex set V, right, we are saying that chromatic number of G induced on A is the click number of G induced on A, right, for every subset. So such graphs are called perfect graphs. So the first immediate example you can think about is bipartite graph, right? So bipartite graphs are perfect graphs because graph is bipartite. Then we know that its chromatic number is 2, right, if there is an edge, right? So the moment we have an edge, its click number is 2, and the chromatic number is also 2 because you need at least 2 colors. And the only case, when the chromatic number can reduce is if there is no edge. And if there is no edge, then we know that the click number is 1 suddenly, right? So for those induced subgraphs where there is no edge, the chromatic number will be again equal to click number because the click number is actually going to be equal to 1. So bipartite graphs are perfect. Then I asked you to show that the complement of bipartite graphs have this property, right? Which means that they are also perfect. So I want you to, if you have not solved it before, solved it yet, please try to go back and try to come up with a proof. And if you are unable to come up with a proof, get back to me and we will see what to do about it. Okay, so bipartite graphs are perfect. Then yeah. Its complements are also perfect. I have mentioned that also. Now we want to prove that interval graphs are perfect. So the reason that we defined interval graphs at this moment is to actually show that they are perfect graphs. Now, how do you prove this, right? So we are going to prove that interval graphs are perfect. Okay, so I would like to get your ideas on this. If you want to try to help me improve this. Uh, any suggestions you have? Are fine. So we want to show that interval graphs. So we already know interval graphs are hereditary. That if you take induced subgraphs, you still get interval graph, right? So if you show that for an arbitrary interval graphs, its chromatic number is equal to its clique number, then we are done, right? So we just need to show that for any arbitrary interval graphs, the chromatic number will be equal to clique number, and therefore this property will carry over like for every induced subgraph because they are also interval graphs. So we just need to show that for an arbitrary given interval graphs, its chromatic number will be equal to its clique number. Okay, let me give you some, let us see, some suggestion. So you know about, greedy coloring algorithm that we have come up with, right? So the greedy algorithm is an algorithm which basically produces, some proper coloring, right? Some proper coloring. Now, what I claim is that if you take an interval graph, there is a way to run the greedy algorithm such that the greedy algorithm always gives the a coloring with the with only the number of vertices in the largest clique in this graph. Okay, so if you start with an interval graph and you give you run the greedy algorithm in a particular fashion, one can show that you will only use the maximum number of colors that you are going to use will be actually equal to the clique number, right? And since the greedy algorithm always outputs a proper coloring, we know that the chromatic number actually is at most the number that is output, right? And we know that it's going to be equal to the clique number, then we are done, right? Because the chromatic number is now equal to clique number. So the question is that how do you run the greedy algorithm? Because you already know what the greedy algorithm does, right? So you just need to decide how to run it. Yeah, so that is a good suggestion. So I would actually try to do the other way that sort by the left point, but yeah, doesn't matter. So I you have the intervals and given an interval graph, right? So if G is interval graph, then G has an interval representation, right? Now, what we will do is that we start by sorting, right? So the intervals going to the appearance of the left endpoint, right? According to the appearance. Left end point of the interval. So, so let us say that for vertex, vi, we have ai, comma bi as the interval. Okay. Then we order, rename the vertices and the interval names such that it basically is increasing according to the AI, right? So A1 is basically less than or equal to A2, less than or equal to etc. AI less than or equal to N. Okay. So this way, so basically, intervals and sort of, right? So, intervals. So this one, two, maybe A2, etc. Then so if two of them, basically are the same, right? Then we just arbitrarily, we can decide, right? We break the tie. Then we call them, one of them F4 and then the other one F5, F6, etc. So we basically sort them according to the starting point of the interval. So now, so you have this. Then what do we do? So we have relabel the vertices and etc. such that V1, having the interval with the least starting point, which is the smallest number, right? V2, etc. Vn, right? So all the n vertices are there. So this, of course, we are going to, like, the idea of sorting is to run the greedy algorithm on this, right? So we are going to run the greedy algorithm according to this order. So use the greedy. So how does the greedy work? The greedy basically picks up the the first vertex that comes to it, and then try to give it the least color which is not used in its neighborhood, right? So let us say that v1, of course, I will color with color 1, right? Then if v2, right? So if you look at the endpoints of this, so we have, like, let's say that a1 and a2, right? I mean a1 and b1. Then we have let's say a2, b2, right? So if v1 and b2 are such that uh, you know uh, they don't intersect, like the corresponding intervals doesn't intersect, then I can give v2 also the color 1, right? So the greedy will always give that also the color 1 because v1 is not in the neighborhood. On the other hand, if they intersect, of course, I will have to use the color 2, right? So if there is some intersection, then we will give the color 2. And then we can assume that, okay, we have done this, as many times as, and we have reached at some point, let's say vk. Okay, so color using D, starting with v1 map to color 1, and v2 map to 1 if intervals corresponding to v1 and v2, right? I v1 and I v2 is empty, right? Otherwise, V2 is mapped to 2. Right? And then suppose we want to color say K plus 1, and we have colored up to Vk, and we want to color Vk plus 1. Now, to color Vk plus 1, what we will do? We will look at the intervals which are intersecting with Vi, and it has got some colors, right? So each of the vertices or the neighbors so the neighbors of Vk plus 1, right? So look at the neighbors of Vk plus 1 which have been colored so far, and look at the set of colors used there, and then find the smallest color that that is available, right? The smallest least index color that is available, and give that color to. So to color Vk plus 1, give the smallest color not used in colored neighbors. This is how the greedy works. So we know that this is how the greedy works. Okay. Now, so you finish when we reach the vertex. Yeah, right. So the greedy outputs a coloring when all n vertices have been colored. Okay. So once all the n vertices have been passed, the greedy will output a proper coloring. Okay. So we know that the greedy produces a coloring. Now the question is, how many colors it used and what is the click number of the graph, right? So the claim is that if the greedy algorithm uses let's say k colors, then the graph contains a click. How to prove this? Any suggestions on how to prove this? Why? Why? I mean, you are right, but you have to tell me why. No, no. See, it will definitely intersect k minus one other things, but we need to make sure that there is a click of this size, right? Yes. Uh, which endpoint? Okay. So what is the common point to all of this? So the common point to all of this is precisely the point. So let us say that no, yeah, I mean you are right, like no. So let us say that the point, the vertex that we are now looking at, right? So let us look at the first time the color K is used, right? So let us say V T is the is the vertex where the color K is used for the first time. Right? Now, at this time, so if we have like A, T, and BT, right? This is the interval, and we have this interval AT, and on this interval, right, we have used the color K for the first time. Now, if of course we know that if we are introducing a color, which means that its previous neighbors must be using all the colors 1 to k minus 1, right? Which means that there is some intervals. I don't know which order. Like so, we have like let's say that v I1, v I2, right? I mean, yeah, that's v I k minus 1, right? So this is basically some subset of vertices, right? Which has appeared before, right? T, right? So the I1 etc. I k minus 1 are less than or equal to 1, less than T, right? So so we have this and this interval we have, right? And some of them, of course, in between have started and finished. But of all these intervals, right? They are intersecting with ATBT. So which means what? If they are intersecting with ATBT and they were chosen before T was chosen, right? Which means that they must have started before AT itself, right? So otherwise, I would have chosen AT before that, right? So since they have started before and they are still continuing, the point AT must be common to all of them. Right? The starting point must be common to all of these intervals, and that is the only reason they are intersecting with this. And we have k minus one of them; they are intersecting, and which means that since this point is common to all of them, they are all intersecting, and therefore they form a clique. And that's why we have a clique cosine scale. So the uh, the interval v interval ATBD corresponding to VT must have some k minus one intervals that were chosen before uh, before VT that are intersecting. Since all of their points All the endpoints are all of their endpoints are so since all of their endpoints are not endpoints like starting points, right? All of their starting points starting points yeah before they all must or they must contain AD, right? So that they intersect with uh, they intersect with uh, the interval ATP. Okay, so just a moment. So yeah, this completes the proof, and